What if Earth was not built from scratch, but from the cosmic leftovers of other worlds? Today, we'll explore how the universe might have upcycled billions of years of cosmic debris to create the planet we call home, and why this idea challenges everything we thought we knew about Earth's origin. Chapter 1. The birth of a solar system. Imagine this. 4.6 billion years ago, there was no Earth, no moon, no oceans, no blue sky. The place where our planet now orbits was just empty space, drifting inside a much larger, chaotic neighborhood. In the center of that neighborhood, a young star was waking up. The sun. It wasn't the warm, stable sun we know today. Back then, it was a newborn star, blazing with unstable energy, surrounded by a vast swirling cloud of gas and dust. Scientists call this cloud a protoplanetary disk. It was made from the ashes of ancient stars, stars that had lived, burned through their fuel, and died in colossal explosions called supernova. Those explosions scattered heavy elements into space: iron, silicon, carbon, oxygen. In other words, the basic ingredients of worlds. These elements drifted together under the pull of gravity, forming the massive rotating disk around our young sun. Now, here's the first twist in our story. The matter in this disk wasn't brand new. Every grain of dust, every speck of rock, every molecule of gas had been part of something else before. Maybe a planet that no longer exists. Maybe the heart of an ancient star. Maybe even the surface of a moon that was shattered long before the sun was born. The universe doesn't waste material. It reuses, recycles, and reshapes. In a way, our solar system began as a giant cosmic recycling project. Inside the disk, tiny particles started colliding. At first, they stuck together thanks to static electricity, forming small clumps. Over time, those clumps grew into larger chunks, and those chunks became even bigger bodies, some just a few kilometers wide, others hundreds of kilometers across. These were the planetesimals, the seeds of future planets. The traditional story says that these planetesimals kept crashing into each other, merging into larger and larger bodies until planets were formed. And in some ways, that's true. But modern computer models reveal a surprising detail. These collisions were often incredibly destructive. When two large bodies slammed together, the impact could shatter them completely, sending fragments flying back into space. Instead of building planets in one smooth process, the early solar system was more like a demolition site, where worlds were constantly being broken apart and rebuilt from the pieces. Think about that for a moment. If Earth formed in this environment, it means our planet was likely assembled from the remains of other proto-worlds that didn't survive. The rocks beneath your feet could be fragments of planets that once orbited the sun, or even fragments from other star systems, mixed in with local debris. During this chaotic era, gravity played the role of a patient but relentless sculptor. It kept pulling material inward, gathering more mass, even as collisions scattered chunks into space. Some of these fragments were lost forever, ejected into the cold reaches beyond the planets. Others fell into the sun, disappearing in a burst of heat and light. But enough debris stayed in orbit, clumping together again and again, slowly growing into the rocky planets we know today. Mercury, Venus, Earth, and Mars. Our planet's own growth was messy. Instead of a clean linear process, it was a patchwork assembly. Each major impact not only added mass but also changed Earth's chemistry. Some collisions may have delivered metals to the core. Others may have brought water in the form of ice, hidden in the interiors of comets and small icy bodies. Even in its earliest days, Earth was already an upcycled world, made from countless older pieces. This perspective changes how we think about our home. We tend to imagine Earth as something that was born in one moment, like a single event in time. But the truth is more complicated. Earth wasn't born. It was built, layer by layer, from the debris of cosmic history. And if we look closely, traces of that history are still here. Meteorites that fall to Earth today are ancient leftovers from that same era. When scientists study them, they find clues about the building blocks of our planet, minerals and isotopes that match the oldest rocks on Earth, and even materials that predate our solar system itself. Some tiny grains inside meteorites are more than 7 billion years old. meaning they existed long before our sun ever lit up. So, in the opening chapter of Earth's story, the key idea is this: our planet was never made from new matter. Every atom in your body, every rock in the mountains, every drop of water in the ocean has been used before. The iron in your blood may have once been at the core of a dead star. The calcium in your bones might have been forged in the heart of a supernova. The oxygen you breathe could have drifted through interstellar space for billions of years before settling here. It's a humbling thought. We live on a world that is not just old, but ancient in every possible way. And yet, the solar system's early years were not peaceful. They were violent, unpredictable, and full of destruction. Earth's survival wasn't guaranteed. The young sun was still unstable, sending out fierce bursts of radiation. Large impacts could have ended our planet's growth at any moment. But somehow, through this chaos, gravity kept pulling the pieces together. By the end of this first stage, the sun had cleared most of the leftover gas from the disk. The larger planets had taken shape, and Earth, still young, still molten in many places, had reached nearly its full size. But it was far from the world we know today. Its surface was a hostile mix of lava flows and cratered highlands. Its atmosphere was thick with carbon dioxide, methane, and ammonia. There was no oxygen to breathe, and no oceans yet to cross. Still, the foundation had been set. Earth now existed as a complete planet, but its journey was just beginning. Over the next hundreds of millions of years, it would face more collisions, more chemical changes, and eventually, the first stirrings of life. All of it built on the same principle that shaped its birth: the universe's habit of reusing what it already has. When we think about the phrase upcycling, we usually imagine turning old furniture into something new, or reusing materials to make art. But in the cosmic sense, upcycling is far more dramatic. It's about turning the wreckage of stars and worlds into something completely new. In our case, a planet capable of hosting life. That's the hidden truth about our beginnings. Earth is not the first chapter of its own story. It's a sequel, written from the fragments of countless other worlds. And if we want to understand how life began here, we have to start by accepting that our planet's very existence is the result of billions of years of recycling on a universal scale. This is the stage on which the rest of Earth's history will play out. A planet born from chaos, shaped by collisions, and assembled from the ruins of the cosmos. The next chapter will take us deeper into that chaos, to see how those destructive impacts may have been just as important for life's future as they were for building the planet itself. Chapter 3. The Archean Aeon. A planet still in the making, the scene shifts. Earth is no longer just a glowing ball of molten rock. Its crust is hardened in places, and vast oceans spread under a sky heavy with volcanic haze. The time is around 4 billion years ago, deep in what we call the Archean Aeon. On the surface, it might look like our planet has arrived. The crust is here, water covers large parts of the globe, and the first signs of stability seem to emerge. But in reality, Earth is still under construction, not in appearance, but in essence. The atmosphere is nothing like the one we breathe today. There is no oxygen, at least not in a form that could sustain life as we know it. Instead, the air is thick with carbon dioxide, methane, and nitrogen. Volcanic eruptions are constant, belching out gases and ash that veil the young sun. The seas are dark, perhaps even greenish, rich with dissolved minerals. And from above, the calm is repeatedly broken by flashes of fire. Meteorites still rain down, some small, others large enough to shake the entire planet. These impacts are not just destructive, they are deliveries, packages from across the solar system, and perhaps beyond. Each collision brings rock, metal, ice, and more importantly, chemistry. Some of these incoming objects are water-rich, adding to the oceans. Others carry complex molecules, carbon compounds that, in the right conditions, can form the building blocks of life. We often think of Earth's formation as a process that ended once the planet reached its current size. But the truth is more layered. The Archean shows us that the planet's assembly line was still running long after its bulk was in place. Scientists studying ancient rocks from this era have found clues that support this extended construction phase. Isotopic fingerprints, subtle variations in elements like oxygen and hydrogen, suggest that Earth's water did not all come from one source. Some matches the signature of comets, others aligned with certain types of asteroids. This mix implies a complex supply chain, where different celestial bodies contributed to the final inventory of Earth's oceans. It's a kind of cosmic blending, like mixing different vintages of wine into a single bottle. Except here, the bottle is a planet, and water wasn't the only delivery. Studies of ancient sedimentary rocks and minerals such as zircon crystals, some over 4 billion years old, reveal traces of elements and isotopes that point to extraterrestrial origins. Certain noble gases, like xenon, carry ratios that are hard to explain if Earth's matter had all formed in place. They hint at repeated injections of material from space, even hundreds of millions of years after the planet first coalesced. Imagine Earth during the Archean not as a finished home, but as a house with workers still coming and going, adding rooms, reinforcing walls, and installing new systems. Meteorites could have delivered not only raw materials, but also triggered massive changes in the planet's surface and climate. A large enough impact could vaporize seawater, inject minerals into the atmosphere, and even alter the chemistry of the oceans. Over time, these events reshaped the environmental conditions in which early life would one day appear. One striking example comes from sulfur isotopes in rocks from the Archean. These patterns suggest that ultraviolet light from the sun interacted with volcanic gases in a way that only happens when there's no oxygen-rich ozone layer. This is a window into the atmosphere's composition, showing a planet still chemically unstable, open to transformation. Each impact could have nudged that chemistry in a new direction, adding ingredients or triggering reactions that moved Earth closer to habitability. And while the heavy bombardment phase, the so-called late heavy bombardment, may have tapered off by the start of the Archean, space was far from quiet. The solar system was still a dynamic, chaotic place. Asteroids and comets followed eccentric paths, some crossing Earth's orbit. The gravitational pull of the giant planets could fling debris inward, ensuring that Earth remained a target. It was an era when the boundaries between finished and unfinished blurred. Geology also played its part in this unfinished story. The crust we see forming in the Archean was thin, fractured, and recycled constantly by tectonic and volcanic activity. Plate tectonics as we know it today may have been in its infancy, but the constant churning meant that whatever the cosmos delivered rarely stayed on the surface for long. Materials could be buried deep, altered by heat and pressure, and then brought back up in volcanic eruptions, mixing the cosmic with the terrestrial in a literal sense. Even the oceans themselves were chemical laboratories, influenced by what fell from the sky. Iron-rich meteorites dissolved into seawater, giving it a distinct chemistry that would later play a role in the energy systems of early microbes. Some scientists believe that without these spaceborne metals, certain biological pathways might never have been possible. So when we think of the Archean Earth, we should not imagine a quiet world slowly waiting for life to appear. It was more like a workshop, where materials were still arriving, being tested, broken down, and rebuilt. Each cosmic delivery was an experiment, and the results were stored in the planet's deep geological memory, in isotope ratios, in mineral structures, in the elemental mix of the oceans and atmosphere. This view challenges the tidy textbook narrative of a planet that formed, cooled, and then simply was. Instead, the evidence points to a more dynamic and prolonged creation process. Earth, during the Archean, was still a canvas, with the brushstrokes coming not only from its internal forces, but from the wider solar system. The final planet, the one that would eventually host life, was the product of both local and imported materials, blended over hundreds of millions of years. And perhaps the most important takeaway from this chapter is the sense of continuity. Even in this early epoch, Earth's story is part of a larger network of cosmic events. The rocks under our feet, the water in our seas, and even the air we breathe today carry traces of worlds that no longer exist, shattered and scattered long before our planet was born. The Archean Eon is the bridge between that violent past and the stable conditions life would one day require. It is proof that a planet's birth is not a single moment, but an ongoing conversation between space and stone, sky and sea. Chapter 2: Accretion or Destruction. We've all heard the classic version of planet formation. Small rocks in the protoplanetary disk slowly stick together, growing bigger with every collision, until they become planets. It's simple, elegant, and easy to imagine. But reality is far more violent, and far less certain. The early solar system wasn't a quiet place where objects politely merged together. It was a battlefield. Picture countless rocky bodies, some the size of mountains, others as large as moons, all moving at incredible speeds. When they met, they didn't always embrace. More often, they slammed into each other with unimaginable force, enough to shatter solid rock, vaporize metal, and send molten fragments spraying into space. For decades, scientists believed these collisions were mostly constructive. They thought that the majority of impacts added mass, making planets grow. But as computer models became more advanced, researchers noticed something strange. When they simulated the conditions of the early solar system in detail, they found that most collisions at those speeds were not building planets at all. They were destroying them. In these simulations, many protoplanets never got the chance to mature. They formed, they grew, and then they were torn apart in catastrophic impacts. They remained scattered across space. Some fragments drifted away forever. Others were pulled into different orbits, only to collide with something else later. The picture that emerged was not one of steady construction, but of endless demolition and reconstruction. This means Earth may have been built and rebuilt multiple times. Its earliest forms could have been shattered, remade, and shattered again. The planet beneath us today could be the final version in a long line of failed attempts, each one leaving behind material that was reused in the next. That's cosmic upcycling on the grandest scale. Here's a thought. The core of our planet might not be entirely ours. It could contain pieces from multiple proto-worlds that once orbited the Sun. Some of those worlds may have been rich in metals, others in ice or silicates. Every time one of them was destroyed, its ingredients were mixed into the growing Earth. Our planet is like a recipe that's been rewritten over and over, with new ingredients added after each disaster. One of the most dramatic examples of this process is the giant impact hypothesis, the idea that a Mars-sized body, often called Theia, collided with the young Earth. This collision is believed to have created our moon. It wasn't a gentle meeting. Theia slammed into Earth at more than 15,000 miles per hour, releasing more energy than any explosion in human history could match. The impact tore away a massive amount of Earth's surface, flinging molten rock into orbit. That debris eventually coalesced into the moon. If this event happened, and most evidence suggests it did, then it is proof that destruction can lead to creation. Without that catastrophic impact, Earth would be a different planet. The moon stabilizes our planet's tilt, influences our tides, and may even have played a role in the development of life. In other words, a violent act of cosmic destruction ended up shaping the conditions for everything that followed. This destruction leads to creation pattern repeats throughout Earth's early history. Each major impact didn't just break things apart. It changed the planet's chemistry and structure. Some impacts may have brought volatile compounds like water and carbon dioxide. Others may have stripped away lighter materials, leaving behind a denser world. In this way, the early solar system was not just assembling planets, it was refining them. Modern research into meteorites supports this idea. Some meteorites contain high-temperature minerals that could only have formed deep inside large differentiated bodies, meaning those bodies must have existed, been destroyed, and scattered their remains. When those minerals are found on Earth, they tell a story of worlds that lived briefly and died violently. Their fragments now part of our own geology. The accretion model, then, is only half the truth. Yes, objects did come together under gravity, but they also came apart, over and over again. The planet we live on is the result of a cycle of assembly, destruction, and reassembly. That's not the tidy step-by-step process we learned in school. It's more like a series of chaotic experiments, with gravity as the only constant force, gathering and regathering material until something stable finally emerged. This understanding changes the way we think about planetary uniqueness. If Earth is the product of repeated destruction, then it's unlikely to be the only planet with such a history. The same cycle could be happening right now in young star systems across the galaxy. Somewhere out there, another planet might be in its third version, halfway through its own reconstruction after a massive collision. It also changes how we think about planetary survival. When we look at Earth today, it feels permanent, unshakable. But in the context of its history, it's the survivor of countless near-deaths. The fact that it made it through the early chaos at all is remarkable. Many proto-worlds didn't. They were either consumed by the sun, torn apart by impacts, or ejected into the darkness beyond the planets. Earth could easily have shared their fate. The lesson here is that destruction is not always the end. In the early solar system, destruction was part of the creative process. It reshaped the ingredients, redistributed resources, and made new combinations possible. Without those cycles of ruin and renewal, our planet might not have the balance of elements, the amount of water, or the protective moon that we rely on today. As we move forward in this story, keep that in mind. Earth's early history was not a gentle climb toward habitability. It was a brutal, unpredictable game of survival, where the winners weren't the biggest or the strongest, but the ones that could endure the chaos long enough to evolve into something stable. In the next chapter, we'll see how this stability finally began to emerge, and how, even then, the planet remained a hostile alien place. The Archean Eon was when Earth began to resemble the world we know, but it was still far from welcoming. And yet, hidden within that hostile environment, the seeds of life were about to be sown. Chapter 4. Upcycling for life. If Earth was assembled from cosmic leftovers, it is natural to ask a deeper question. Could those leftovers have also prepared the chemistry that led to life? For a long time, the common picture was local. Warm ponds, lightning, volcanoes, and deep-sea vents were treated as the main stage. That story is still powerful, yet evidence keeps pointing to a wider supply chain. Space did not only deliver rock and ice, it also delivered ready-made molecules, reactive minerals, and energy pulses that nudged simple chemistry toward biology. In short, the universe may have upcycled ancient matter into living matter. Let's start with ingredients. Many meteorites contain amino acids, simple sugars, carboxylic acids, and even building blocks related to nucleobases. Comets carry water and organics trapped in ice. In the cold of interstellar clouds, carbon monoxide, water, ammonia, and methanol can react on dust grains under ultraviolet light to form complex organics. Those products can be packed into rocks and ices and shipped across space for millions of years. When these objects fall to Earth, some of the cargo survives. Laboratory shots that mimic impacts show that shocks can both spare delicate molecules and sometimes even help them bond into longer chains. Destruction and creation travel together. Now consider catalysts. Life needs more than raw material. It needs surfaces and metals that speed up reactions. Meteorites are rich in iron, nickel, and trace metals such as cobalt. A common meteoritic mineral, a phosphorus-bearing alloy found in iron meteorites, can release reactive phosphorus when it meets water. Reactive phosphorus is crucial for forming energy carriers and backbones of genetic molecules. Other meteoritic grains host tiny catalytic surfaces that promote hydrogenation and polymerization. In a young ocean filled with dissolved iron, sulfur, and silica, each fragment from space was a portable laboratory bench. Energy sources were everywhere. Ultraviolet light from a thinner oxygen-poor sky rained onto shallow waters. Lightning flashed through stormy air. Hydrothermal vents pumped heat and chemical gradients from the seafloor. Impacts themselves delivered extreme but brief bursts of pressure and temperature. None of these sources alone writes the full recipe. Together they produced cycles: heating and cooling, wetting and drying, oxidation and reduction. Chemistry grows in cycles. Reactions that stall under steady conditions can advance when the environment pulses. Where might this chemistry have taken place? Two settings stand out. The first is the deep ocean, at alkaline hydrothermal vents. There, warm fluids rich in hydrogen met cooler, more acidic seawater. Natural chimneys made of iron and sulfur-bearing minerals formed porous mazes. creating thin barriers that separated fluids with different pH and redox states. Those barriers act like primitive membranes and can drive the first energy conversions. Meteorite-derived metals and phosphorus dissolved into this environment would have strengthened the vent's catalytic toolkit. The second setting is on land, at hot springs and tidal flats. Clay minerals, evaporating ponds, and volcanic ash create surfaces that help small molecules line up and link into polymers. Wet-dry cycles in these places encourage strands to grow, then fold, then grow again. Fatty acids found in some meteorite scans self-assemble into tiny bubbles in water. With repeated drying and rehydration, these bubbles can trap strands and small catalysts, forming protocell-like compartments. In such niches, space-delivered lipids and organics do not replace Earth chemistry, they boost it. This brings us to the key reversal in the narrative. The older model treated early life as almost entirely homegrown. The updated view sees two toolkits working together. One toolkit is endogenous, volcanism, lightning, vents, minerals, and cycles produced on Earth. The other toolkit is exogenous, organics, metals, reactive phosphorus, and water delivered by asteroids and comets. Upcycling is the bridge. The universe did not send us finished cells. It sent parts that had already been processed by starlight, by the cold of space, and by earlier rounds of chemistry on other bodies. Earth then reused and refined those parts. Clues for this blended origin show up in subtle places. Hydrogen isotopes in our water point to a mixture of sources. Noble gas ratios hint at repeated additions from outside. Some prebiotic pathways run far more efficiently when boron, molybdenum, or nickel are present in the right forms elements that meteorites readily supply. Even the balance of carbon types in very ancient rocks can be read as the footprints of early organic reactions, later overprinted by life. None of these fingerprints alone proves the whole story, but together they form a pattern that favors partnership rather than isolation. Timing matters. Could impacts sterilize the surface? Yes, the biggest ones did, but between major impacts were long quiet windows, thousands to millions of years, when oceans and crusts stabilized and chemistry could advance. After each large collision, fresh surfaces formed, new minerals were exposed, and nutrients rained from the sky. Periods of destruction reset the board, but they also recharged it. The early Earth was not a steady laboratory. It was a laboratory that cleaned and restocked itself over and over. Another question is order. Which came first? Compartments, metabolism, or information? We may not need a single answer. Invent systems, network like metabolism. First chemistry could have emerged, with carbon dioxide, hydrogen, and minerals driving small cycles that store and release energy. In hot springs, compartments. First chemistry could have dominated, with lipid bubbles capturing polymers. Space inputs feed both paths, supplying lipids for compartments and metals and phosphorus for energy chemistry. When those paths met, they could support one another. Containers protect reaction networks. Networks supply building blocks that help membranes grow. What about the leap to encoded information? Simple strands can copy imperfectly on warm mineral surfaces during dry phases, then spread during wet phases. If meteoritic organics and Earth-made molecules both contribute to the pool, the chance that a few templates become self-reinforcing increases. Copying with variation invites selection. Over many cycles, more stable and more efficient variants accumulate. The system moves from chemistry that happens to chemistry that persists. This picture reframes the famous origin gap. We often imagine a single spark in a single pond. A more realistic view is distributed and patient. Many places hosted partial solutions. Some produced compartments. Some produced energy cycles. Some produced longer strands. Most of these experiments failed. A few combined. The combinations that held together longest gained access to more resources and more cycles. Cosmic upcycling widened the search space and shortened the waiting time by dropping in components that Earth did not have to reinvent from scratch. There is also a philosophical turn here. If life's first steps used matter processed on other worlds, then our ancestry is not limited to this planet. Our story includes dead stars that forged our atoms, icy bodies that ferried organics, and shattered worlds that donated metals. We are local beings with non-local roots. That idea is not only poetic, it guides where we look next. If upcycling helped here, it can help elsewhere. Young planets around other stars will also sit under ultraviolet skies, host vents and hot springs, and be bombarded by organics-bearing debris. The same partnership can play out again. Does that mean life is inevitable? Not necessarily. Conditions still have to align. Too many giant impacts in a row can erase progress. Too little water or too few minerals can stall key steps. But the combined toolkit makes success more likely across many trials. Think of the universe as a patient engineer. It builds, breaks, and rebuilds. It keeps the parts that work and feeds them forward. Earth's biosphere is one successful prototype in a vast workshop. So, would life have started without cosmic recycling? Maybe, but probably later, and with more difficulty. Upcycled materials did not write the script by themselves. They supplied pages already printed with useful lines. Earth edited those lines into a coherent chapter. That partnership sped up the plot. As this chapter closes, the stage is set. The planet's chemistry is rich. Compartments form and break. Energy flows through mineral networks. Information begins to copy with variation. None of it is yet life as we define it, but all of it points forward. In the next chapter we will step back and reconsider what this means for Earth's identity. If our world is a patchwork built from many others, then our place in the cosmos is different from what we learned in school. We are not a closed case. We are a living summary of the universe's long habit of reuse. Chapter 5: Rethinking Earth's Identity. When we look up at the night sky and see Earth from the perspective of space exploration images, the blue marble floating in a sea of darkness, we tend to think of it as a singular entity, a unique world born from a specific chain of events that could never be repeated. But the idea that our planet may be a mosaic of ancient cosmic fragments changes that view entirely. It tells us that Earth is not a product of a single origin story, but rather the result of countless histories merging into one. If the building blocks that formed Earth came from the shattered remains of other worlds, then our planet is not an isolated masterpiece. It's a cosmic collage. Imagine walking across a beach, picking up different stones. Some are smooth from eons in the water, others jagged from recent fractures. Each one has its own origin. Some might have come from mountains far away, others from volcanic eruptions deep within the planet. Now imagine that instead of pebbles, you're holding entire planetary fragments. That's what Earth may be. A beach where the tide of the universe has deposited pieces from countless past worlds, now bound together into one. This realization forces a profound shift in perspective. It means that our oceans, mountains, and even the air we breathe may be the legacy of worlds long gone. Water, for instance, could have been delivered by icy asteroids from the outer solar system, or even beyond it, carrying with them not only H2O, but also the organic compounds that would later seed life. The iron in our blood may have once been part of the molten core of a completely different planet that no longer exists. The silicon in our technology may have crystallized in the crust of an ancient world before being scattered by a cataclysmic impact and recycled into our own. If this process is common in the universe, if planets routinely form from the debris of others, then Earth is not an exception, but part of a cosmic cycle. Across the galaxy, young stars are surrounded by swirling disks of gas and dust, the birthplaces of new planets. But those disks are not made purely from scratch. They are infused with material from previous generations of stars and planets, remnants of long-extinct worlds. Over billions of years, collisions and mergers reassemble these fragments into new configurations. That means somewhere out there, right now, other Earths are taking shape. Planets built from pieces of multiple worlds, just like ours. This raises an exciting possibility for astrobiology. If the mixing of planetary debris is common, it increases the likelihood that young worlds will inherit complex chemistry right from the start. Instead of having to generate all the ingredients for life from scratch, they may be born with a ready-made recipe: water, carbon, nitrogen, and a variety of minerals already blended together. That could make habitable planets, and potentially life, much more common than we once imagined. But the implications are not just scientific, they are philosophical. We like to think of ourselves as earthlings, as if our identity is tied to one planet alone. Yet the truth may be that we are children of the cosmos itself. The atoms in our bodies have traveled unimaginable distances over billions of years. Some may have once been part of a comet that sailed between the stars. Others may have been locked in the heart of a supernova before being flung into the galaxy. They came together for a brief moment in cosmic history to form us. In this sense, we are not simply from Earth, we are from everywhere. The story of our existence is not just the story of one planet, but the story of an entire galaxy's worth of events. Stars being born and dying, planets colliding and reforming cosmic debris, drifting until gravity found it and pulled it together again. Without that chain of destruction and rebirth, there would be no Earth, no oceans, no continents, and no life to tell the tale. And this knowledge should change the way we think about the future. If our world is the product of countless past worlds, then what we do here will ripple forward into countless futures. The elements that make up our cities, our forests, our bodies, they will not remain here forever. In billions of years, long after our sun has burned its last fuel, Earth will no longer exist as we know it. Its materials will be scattered back into space, to one day become part of another planet orbiting another star. Life, in some form, may continue there, carrying with it a tiny piece of what once was our home. So the next time you look at the night sky, try to see it not as a vast emptiness, but as a living network of connections. Every star, every faint point of light, is part of the same story. Somewhere out there, the raw materials for future planets are drifting, waiting to be gathered into something new. A billion years from now, they may be the soil of an alien garden, the metal in an alien city, or even the bones of alien beings wondering about their origins, just as we wonder about ours. This is what it means to rethink Earth's identity. Our planet is not a closed chapter, but a page in an unending cosmic book. We are part of a chain that stretches both backward and forward in time, linking us to worlds we will never see and to futures we cannot yet imagine. And in that chain, there is no true beginning or end, only transformation. If this journey into the hidden origins of our planet has changed the way you see Earth, then perhaps the most important thing we can do is to care for this fragile, temporary home. Because while Earth will one day be scattered into the cosmos again, what we do now will determine the legacy we leave for whatever comes next. And so, as we stand here, on this improbable mosaic of ancient worlds, let's remember that our story is written not just in the rocks beneath our feet, but in the stars above our heads. If this journey into Earth's hidden origins made you think differently about our place in the cosmos, consider liking this video, subscribing for more science stories, and sharing your thoughts in the comments. I'd love to hear them.